lot to think about, and he always raises a lot of questions. He could speak for hours, and it's something really valuable for all of us. I always feel like I'm back in class in college when I hear Len speak. Anyhow, Len Goldman went to my alma mater, Rutgers University in New Jersey. He graduated in '63. Oh, the same year I graduated, '63. Yep. And then he went to University of Pittsburgh for his PhD degree in nuclear physics. So he's been working for the last 50 years in designing and building electronic systems, ranging from the first CAT scans in nuclear medicine, in oil and uranium exploration instruments, fiber optic connectors, and currently developing guidance systems and missiles. So today he's going to teach us a little bit about a popular subject, but I'm sure we're going to hear a little bit more in-depth discussion. I hope we can all understand it. He dumbs it down for us so we can follow it, about climate change. Len, thanks for being here.
By the way, I did mention my friend who was my first boss, 102 years old, also a nuclear physicist, which proves conclusively that radiation is good for your health.
And what's his name?
Jay Tippin. Jay Tippin, over at the top. Okay, so let's start. We're talking about today is global warming. And I'm going to divide my talk into like 3 sections. First is define the problem. What is it? What's happening? The second is determine the cause of the problem. Well, determine the cause of the effect. Let's not say even give it a problem. And the last group is proposing solutions for cleaning it up. So, I'll just click this to get the next one. Yeah. All right, next is first that's proof of global warming. Where is it? I'm clicking, but it's, there it goes. All right, here's the first of a series of graphs. This is the average temperature for the whole world for each year, starting in 1880 and working its way up to the current day. And you can see that it was growing slowly in the first century, but since about 1960, it's been accelerating and growing at a rate of a couple of degrees, you know, and this is also only good to 2020, and the last couple of years have even been hotter. So the temperature is rising. That's, whoops, wrong way. Sorry. This also is showing some more about the heating, but here you see the graphs are showing for the whole year, month by month, and you can read by the color, you can see the hottest one, of course, is 2023, and you can see the gap, the step up is getting bigger and bigger. And this was only through August of 23, and you know, this August was very hot. So when the new data comes out, it's probably going to even be worse, or higher. I don't say worse, higher. The other effect we're seeing is the Arctic ice coverage. This is the number of I think it's square miles, square kilometers that are covered with ice in the Arctic, and it's declining by about 12% per decade. So it was like 7 units, and now it's down to 4. So it's declining fairly rapidly. And one of the consequences of this, as a child, you remember reading about the Northwest Passage. This was the goal. Everyone died trying to get through the Northwest Passage. Now you can take a cruise ship through the Northwest Passage. So there's definitely something happening. And the last one, a little fuzzy, is the sea level is rising also. It's again from 1880 up to the present time, with the acceleration after the turn of the last century, 1900. Shows my age. I said turn of the century. Never mind. And it's not that fast. It's 2 millimeters per year, so it's about 1 inch every 10 years, but it's accelerating. And it's definitely an effect. Right now, it's not that bad of an effect. So this, therefore, is the effect. I mean, there's no question The earth is warming up, everything's getting warmer, ice is melting, etc. Seas rising. By the way, the reason the seas rise is when water gets warmer, it expands. And the other source is ice. When it melts in the glaciers, they pour water into the ocean. Between the two of them, that's the source of the rise, and that's going to accelerate. So, where does it come from? What's doing it? Well, the sun provides 99.99% of all the energy to keep the earth warm. You think the fossil fuels, we all think, oh, you're burning all these things, the heat from the burning is going to be warming up the earth? Nope. It produces less than 0.001% of the solar energy. It's insignificant. And in fact, there's 4 to 5 times as much heat from geothermal heat. As you know, the Earth, the interior of the Earth is quite hot. In fact, the center is molten iron. This is due to radioactive isotopes left over from the Big Bang. And the heat that comes up is very small. I mean, in a few places it comes up high, but there's always a little bit of heat trickling up, and that heat is 4 to 5 times as much as the heat from burning fossil fuels. So the burning of the fossil fuels itself is not heating up the Earth. Okay, so sun, we now established the sun is the source of our heat. What does the sun put out? Electromagnetic radiation. Electromagnetic radiation is when you have an electric and magnetic field oscillating. When they oscillate, they generate a wave. That wave travels at the speed of light. Thank Mr. Einstein and a few others. And it's constant, but we won't get into that one. And at different frequencies. The frequency is how often the wave goes up and down. And it ranges from kilohertz, which is 1,000 times per second, to gigahertz, a billion times a second, and even higher. The lowest end, let's see, can I get the, no. Do I get it?
Yeah, it's there.
Where? Oh, there it is. No, it's not very big. Anyway, the low end is radio waves on the left, the blue. As you go a little further, you get into microwave, which is a little higher energy, and the energy increases as the frequency increases. Then you get into infrared, which we'll come back to, very important. And then the little piece in the center is the visible spectrum. That's where most of the energy from the sun comes. And our eyes are sensitive to that because evolutionarily it made sense to be able to use the visible light. Our eyes see visible light. Ultraviolet, we don't see, but you stay out in the sun too long, you'll get a nice tan from ultraviolet. So you gotta be really careful. And then there's higher energies from X-rays and gammas, which are not relevant to this discussion. Main thing we're talking about is visible light and infrared, okay? Let's move to the next one. Okay. The sun heats the earth with high energy visible light. You know this. When you're around the sun, you get warm. The earth then heats up. If the earth was just a big block of rock sitting there with nothing else around, the sun will heat it up. Now every object also emits radiation. But the radiation it emits depends on its temperature. The higher the temperature, the more radiation they emit. The sun, being at temperature of thousands of degrees, millions of degrees, really emits a lot of heat. The earth at a couple of 50 or 60 degrees centigrade, emits a little bit of heat, but it's significant, not insignificant. So what happens is, if you had just a big block of rock sitting out in space, sun hitting it, it'll get warm. And more sun, it gets hotter and hotter. But as it gets hotter and hotter, it starts emitting radiation of its own. And more as it gets hotter. And at one point, the amount of energy that it is emitting and sending out into space equals the amount of energy that the sun puts in. And it's stable, but it stabilizes at a temperature. And depending on the characteristics of the rock, the temperature can be quite different. So let's give a good example here. I'll skip this. If I have time, I'll come back to it. Too much physics. This is surface temperature. They're looking at, if you see on the left side, you have asphalt, brick, concrete, sand, rock, metal. If it's sitting out in the sunlight, the asphalt comes up to 166 degrees, while metal only comes up to 144 degrees. We all know that. You go walking out on bare feet, and you walk on a black asphalt, it burns. But nice white sand, white concrete, even metal, because the metal and the white reflect a lot of the heat away, so it doesn't go in. So that's something you can see. And also, if you look on the right side, when you're in shade, it's also pretty much the same temperature. So the characteristics of the surface determine how hot it gets. The asphalt absorbs a lot of the sun's energy, therefore it has to radiate more infrared radiation to keep it from burning up, and only does that by raising its temperature. So that's true if you have a block just sitting there. Unfortunately, the Earth is not just a block. The Earth is surrounded by an atmosphere. So the other word that you've all heard about, the greenhouse effect, along with global warming. What is the greenhouse effect? In a real greenhouse, you have the sun's short waves, the visible light, goes through the glass. It's all enclosed in glass, because glass is transparent. That's why we use glass. And it comes in without any energy loss, and it hits the plants, the earth, everything, and heats them up. And they get very hot. And like the block before, like the asphalt, they start emitting infrared radiation to cool themselves down. Unfortunately, glass acts like a reflection, like a mirror to infrared. The infrared heat cannot escape. It bounces right back down. And so therefore, the temperature gets much higher until eventually, the only way it keeps from burning up is the long wavelengths do go through glass, and they're the ones that are dominating, keeping it cool. Anyone who's ever been in a greenhouse, even in the dead of winter, know how hot it can be. In fact, they keep the windows open sometimes because it really can be burning out. So that is what we call the greenhouse effect. How does it apply to us? We're surrounded by an atmosphere of gas. And this graph here, in the blue area, which I'll try and get, there we go. Okay. This blue area, this is the energy that radiates out to space. This is the cooling effect that the Earth does. It sends out all kinds of energy. The hotter it gets, the more it gives out. However, CO2, carbon dioxide loves infrared radiation. It sucks it up like a sponge. And it captures all the infrared radiation, and like the greenhouse, like the glass, it reflects it back down to the ground. So therefore, the greenhouse effect is the Earth has to get to a higher temperature to increase the amount of radiation in other regions to get the cooling effect. So the CO2 is now it also is a little bit one from water and an even bigger one from oxygen, but the CO2 is the dominant. Just as an aside, the year 1860 was the year without a summer. I don't know if you ever heard about this. It was very cold. The reason was that Mount Tabora in what is now Indonesia erupted and threw an enormous explosion, threw millions of tons of ash into the sky. and it covered the earth. So that instead of we're talking about greenhouse effect, it was the opposite. The ash was blocking the sunlight from coming down. As a consequence, the summer never existed. They were even getting snow in the summer. There was no harvest, 1816, and a lot of famines, a lot of deaths. No one knew why. The southern hemisphere didn't have this problem because 6 months later, when they went to summer, the ash had already dissipated. But this shows you how delicate it is on our atmosphere, how small changes can make big changes. The other thing I'll put in there is a nuclear winter would be much worse. I don't know if you know what the nuclear winter was, but those of us old enough to remember, they forecast that if all the bombs went off, the amount of debris put up in the atmosphere would make Mount Tabora look like a firecracker. And in fact, that is why they passed the law. They all agreed, no more atmospheric testing. All the future testings are underground. Because they all recognized even the small amount of testing they were doing were having really severe effects on the weather. So keep that in mind next time you think there might be a nuclear war. Stock up on your vegetables or something. Oh, back to CO2. So here's a graph with two curves. The blue one is the amount of carbon dioxide in the air going from, I think it's about 1800 up to the present day. And the second, 1751, excuse me. And the other line, the dark line, is the amount of burning of fossil fuel. So it's a very good correlation that the CO2 is due to all the fossil fuels we've been burning: wood, coal, gas, oil, and that's where it's coming from. And it gets pretty high. Okay, now let's take a look back in time. The scale on the bottom is in hundreds of millions of years, 500 million years, a short time. And the red line is the CO2 concentration and the blue line is the temperature. The correlation is not as good as the CO I just showed you, but generally when the carbon dioxide concentration is high, the temperature is high, and vice versa. But more important is to see right here, if I can get it. Oops, sorry. How do I go back up? The right click should go back. No. Oh, I see. Previous. Okay. Let's take a look all the way at the end, which is the current time. Remember, 500 million year graph, so I mean but you notice that both the temperature and the carbon dioxide are plummeting. We are actually now the coldest the Earth has been and the lowest concentration of carbon dioxide, except for this area back at 300 million years, which had other problems from volcanoes, but that's beside the point. But it's really dropping. And so some people are saying, well, maybe it's coming back. The only problem with that is these curves showing rise and fall, are measured in millions of years. It's not a rapid thing. There's an old joke about a geologist came to a small town and gave a talk and said, in 3 billion years, our sun will go supernova and incinerate the Earth. So some guy raised his hand and said, did you say 3 billion or 3 million? He said, I said 3 billion. Oh, good, I was worried. Always put it in. So let's do the summary. CO2 is the most probable cause of global warming. Think of it as, in our legal system, the CO2 would have been arrested, indicted, and brought to trial. And so it's pretty clear. Not 100%, but nothing is 100%. The short-term effects is already obvious: warmer summers, snow-free winters, low-lying, whoops, can't spell line, areas being flooded. I blame that on my 102-year-old guy. He missed that.
At 102, you can make a mistake or two.
Yes, you're right. And the long term is that we'll have tropical climate worldwide. No ice, I mean, we'll have growing plants in the North Pole. Sea level will rise, we measured in hundreds of feet, which makes Balakinwood an island. But that's like my other joke. Did I say, you know, a billion or a million? It'll take quite a while. But in the short term, though, is enough to cause us problems, serious problems, especially for low-lying areas. Okay, now the last thing, solution. What should we do? Well, the first thing is do nothing and just adjust to the change in climate. We can wait until the fossil fuels run out. They are fossils, they will run out. And people always say, you know, they're always predicting when they're going to run out. It'll be a long time before they run out, but we're already running out of cheap oil and gas. Now, you know, it costs $1 billion to drill a well, and the cost of finding more, you know, oil and gas is going up. So in time, it won't be we would stop using it. We just can't afford to use it any more than we would use wood for heating. You know, the wood, you wouldn't go out and cut up all your furniture and burn it to keep warm. You have better uses for wood these days. So that's also, you can adjust your agriculture by going to different types of plants. It's already happening. The wheat zone in the Midwest has moved, I think, about 100 miles north into Canada. And the southern part is no longer doing wheat, but they're doing more tropical, you know, kind of plants that will go in, you know, things grow in the jungle very well. So you have to adjust, and with that we can do that in the short term. And you have to protect the low-lying coastal areas, which I'll get into later, but that's also going to get worse and worse. Miami is really going underwater because they have a double whammy. Not only is the sea rising, but Florida is sinking. It's nothing more than a reef of calcium carbonate, and it dissolves. So it's shrinking quite rapidly. Anyway, now what about if we want to reduce or eliminate CO2? Well, the first thing is develop wind, solar, or other renewables, wind and solar being the biggest ones, with the idea being we get our energy without producing CO2. We can improve the fission nuclear power. The current nuclear reactors we have right now are very old designs, 50, 60 years old. The new designs are coming, which are much more efficient and can have a revival and cut the cost down. We can then also develop the fusion nuclear power, and it will require something equivalent to the Manhattan Project that we did for the bomb in World War II. And we can accomplish these goals, everyone feels, by political action. The Paris Accord, you know, it will be legislated. So, okay, we are now, as you know, there are wind turbines everywhere, solar fields everywhere. Does anyone want to guess which state in the United States has the largest amount of wind power?
Iowa.
Close, Texas. And it also has the second largest solar. Oops, no, I want to go back. I'm sorry, what happened? Texas has by far the largest amount of wind power. And Iowa is right behind it, way behind it. And the same thing on the right side for solar power. California is the leader, but Texas is right there, and Florida. Now it's interesting. We all believe that the political action, which wants to do this global warming, get rid of CO2, is mostly, I don't want to get into politics, but generally the blue states would want that, and the red states are sort of opposed to it. This is a map. On the left is wind power. The dark blue is where all the wind power is. And you'll notice that it's all through the Great Plains and the West Coast, a little bit in the Northeast, nothing in the Southeast. And we've been seeing maps like this for the last couple of months through the election, and they're all red and blue. This one's red, that one's red. This is not following any political regime. You're not seeing, Southeast, they have no wind power. You say, oh, because they're Republicans. But look at the whole Midwest, which are Republicans, and they have the biggest amounts. Same thing with the solar. California is the leader, but Texas is right there, and Florida is right behind it. What's going on? This is not being done by political. What's causing it? What's causing it is this. This is the cost of generating electricity. And you can see, I hope I can show you this, but nuclear power is on the right side. I can't get, here it is the most expensive at $155, I think that's per megawatt. And it's been going up. This is a 10-year graph. It was like 123. Coal has stayed pretty constant at 100. Gas has gone down a little bit at 56. But solar and wind are 41 and 40. They're cheaper. These people are doing wind power in Texas and the Midwest because it's cheaper than even gas. And even in Texas, where they have the gas fields right there, it's cheaper. They're not doing it because they believe any Paris Accords or political or by fiat from the government. They're doing it because it's cheaper. And they're doing it big time. The reason that the reason that coal is no longer being used or being phased out, a lot of people think it's because of the pollution. No, it's just too expensive. I mean, the pollution is nice getting rid of it, and nuclear used to be a lot cheaper than fossil fuels. And that's when they built them 50 years ago. But they've gotten more expensive for lots of reasons, and the other ones have gotten cheaper, so they stopped doing it. Economics is driving the energy market. This is not a political thing. I found this very interesting, and this is also, I think, only through last year. If anything, the prices are getting more so. And the gas can go up, because the gas one depends on what the price of gas is. It could easily go up even more. It could go down too, but it could change. The wind and the solar are going to be fairly constant, or getting better as they make them more efficient. So other paths to remove carbon dioxide. We can improve the efficiency of the current fission reactors. These reactors were built and designed 50, 60 years ago, and no new designs have come up. They stopped building them because, like I said, they're expensive. There are new designs coming in that are much more efficient, much smaller. And the other thing too is they're really very safe, except Russia. The amount of accidents in the United States are very limited, and the one right here by us in Harrisburg. But the accident, I think I discussed this in my last talk, was due to poor training of the operators, not anything fundamental. And that's the only major accident. And these have been running for 50 or 60 years. A lot of the cost is because of the fear of nuclear. If there hadn't been a Hiroshima bomb, we'd have a reactor on every corner. Because they're not as dangerous as a refinery or a coal mine or any of the other things. But that's psychological. I won't get into it. And don't go to Russia. I had a good friend who spent 2 years in Russia, helping after Chernobyl, helping them out to get improvement. When he came back, he said, the Russians have made phenomenal improvement in their reactors. They're all the way up to just being dangerous. That's not a joke. Fusion reactors, this is my favorite. There are several types of fusion reactors being developed. At the present time, it looks like within 5 or 10 years, they will have prototypes that make net energy, they call it. They get more energy out than they put in. They say they're doing it now, but that's a lie. They're looking at the energy that's actually put into the chamber, not how much energy they needed to generate that energy that went into the chamber. Okay, but they're getting close. And once they have prototypes, and the procedure is down, then we have to build, this is my opinion, a network of these fusion reactors. They don't have any radiation. They can be very small and compact. They have lots of benefits. And we would need something on the order of a Manhattan project to build thousands of these and get us totally off of fossil fuels. I think I did talk about on my lab, and if you're over here, the problem with the best one, the one I worked on, is they need this isotope of helium called helium-3, which doesn't exist. And they contacted me because you can make it in the cyclotron, which I worked on in graduate school. But that didn't, and they can do prototypes now because it's a byproduct of reactors. So they can get enough just to do experiments. But it turns out, we just found out, a good source is the moon. It turns out the sun puts out enormous amounts of helium-3 because the sun is a fusion reactor, pumps out helium-3. It never makes it to Earth because we have a magnetic field and all the charged particles go around us, and that's why we get the northern lights. You're seeing all those charged particles hitting the atmosphere. Beautiful, but they never make it down here. The moon has no magnetic field, no atmosphere. They've been bombarded for the last 3 billion years with this solar field. And they're finding that a lot of the helium-3 embedded into the rocks. And it's helium, it doesn't make any chemical reaction, not that there's any oxygen there anyway. So they could mine it. And there's enough concentrations there. And if they would bring back the payload that came from Apollo 11, the first Apollo that went there, like the 3 men and their equipment that came back, if they brought back something of the same weight and volume, they could power at least the entire United States, possibly the world, for a year with that much. So, I'm hoping to see that because I think I still have another 20 or 30 years left. But I don't think, but it's, right now it's probably, let's see, whoops, sorry, I didn't mean to do that. That was my end one, but I got it up already. I finally found, I had this other one on the right, and I got a lot of complaints that it was against, women, but I got it from the men down too, that this is proof of global warming. Let's see, I gotta go back.
You showed this before.
Yeah, I showed the other, but I got the men one now, because I wanted to.
Now it's equal rights.
Now it's equal rights, yeah. Okay, here's an example. You don't have to read the details. This is New York City new zoning laws for global warming. What they're requiring is all the low-lying areas in the next 50 years have to put all new construction up on stilts, just like they do on the shore. No living, no utilities, nothing on the ground floor. They have 50 years to do it. They're also planning to raise the street levels as well. And now, whether it's going to work or not, that's not the point. The point is people are thinking, and that's what we're going to have to do. Even if we stopped CO2 production tomorrow, the inertia of what's going on is the Earth will continue warming for quite a while. And of course, we're not gonna stop it. You have to do things like this. Miami is doing a similar one. They're gonna probably be putting up dikes. And you know, anyone you go to the shore, all they talk about is erosion. You know, the beach. They keep on bringing more sand, and you know, and everyone's up on tilt, etc. We'll have to work on that. So that's what we have to do. I was going to show you my nice little picture, but you saw it already. So that I was supposed to go out in a flourish. But any questions?
Maybe one question.
Yeah, we have time for one question.